morning everybody. Today we are back with fluorescence spectroscopy again. So, today we will take up this Exciplex. Last time we had a little introduction on this topic, that is Exciplex. So, today we will talk a little more about Exciplex. Now, the term Exciplex, it contains the significance of the term, that is it is basically your excited plus complex. Okay. So, Xi and this plex. So, it is a complexation in the electronically excited state. So, the point is you have heard about complexation reaction, and those are generally, those are in the ground state, electronic ground state, in the electronic ground state. Now, this complex formation, like example, there could be many examples, like coordination complex, that is copper ammonia complex, or like there are plenty of examples of complexes in the ground state. Now, ground state complexation means there is a definitive minima in the potential energy surface in the ground state when, say, A plus B forms AB. Okay. So, so there is some interaction, and that interaction can be of various types. It may be hydrogen bonded interaction, it may be hydrophobic interaction, it may be electrostatic interaction, it may be a charge transfer interaction, and everything occurs in the ground state, and these are generally called simple complex. But the term Exciplex is something to deal with the electronic excited state, that in the ground state there is no there is no interaction, okay. But the moment you excite the sample, then it goes to the excited state, and there is a some kind of interaction, maybe charge transfer interaction or electron exchange interaction, that brings them these two part close to each other. Okay. So, so Excimer and Exciplex, these are very closely related terms. Now, excimers, excimer is a general term, and it is basically the excimers are dimers in the excited state. Okay, dimer formation in the excited state, and the term excimer results from the that is, the term is from excited dimer, excimer, and they are formed by collision between the excited molecule and an identical unexcited molecule. So, one molecule, say M, another molecule M, so you excite, giving rise to M star, and then these two interacts, maybe it is a collisional interaction leading to your this excimer. So, 1 M plus M, M, this is in the singlet state, okay, and the excitation energy is delocalized in this M framework. When they are interacting, so together these two will form an aggregate, and the excitation energy is delocalized. Okay. The Exciplex is basically it is excited complex, okay, and they are formed by collision of an excited molecule. So, similar kind of thing, excited molecule, it may be an electron donor or an electron acceptor, and with an unlike unexcited molecule, electron acceptor or donor, I mean the reverse. So, if you have say M, or say if you have a say D giving rise to D star, then you have a, so in that case it will first it will form like D A star, and then there is an electron transfer giving rise to D plus A minus, or it may be like D delta plus A delta minus, then this. Okay, so, it is a charge separation, and then a charge transfer complex formation. So, this charge transfer means there is a Coulombic term, there is a Coulombic interaction between plus and minus that holds these two entities, I mean D plus and A minus together. So, you can have, like in that case you can have here donor is excited. It may be that in other situation your acceptor, I mean you have D and you have A, in the ground state there is no interaction, but the moment you excite this, then this excited acceptor accepts an electron from the ground state donor, giving rise to the complex. So, basically what is happening, that you have D plus A star, then electron transfer takes place or charge transfer interaction is taking place, so that it becomes D delta plus, and here I should put a star maybe to indicate that this is the excited one, in here also delta minus, and then ultimately it gives rise to D plus A minus. Okay, so, situation will be like in one case D has to be excited, in other case the acceptor has to be excited to get the exciplex or excited state complex. So, it is a hetero excimer. I mean hetero excimer means, in that case in the excimer or means actual excimer, both the entities are same. I mean one is excited M, another is ground state M, and here it is one excited M and ground state maybe something M primed. The formation of excimers and exciplex, these are very closely related terms. Okay, the formation of excimers and exciplex are diffusion controlled process. So, that means these two entities should come close to each other for the interaction, and then either the excitation energy is delocalized between M prime or M, or it is the charge is transferred from the donor to the acceptor. The photophysical effects are thus detected at relatively high concentrations of the species, so that a sufficient number of collisions can occur during the excited state lifetime of the donor or maybe the acceptor. And temperature, viscosity are of course important parameters. So, if you increase the temperature, then it will have some effect. If you increase the viscosity, then you can also expect to have influence on the formation of this complex. I mean, if the viscosity is high, you can expect that once it is formed, it will stay there for longer time, or it takes time to be formed. Okay. So, you need to have a considerable amount of high concentration, like 10 to the power minus 3 or minus 4 molar solution, 10 raised to the power minus 3 or 10 raised to the power minus 4 molar solution. Okay. And so that there is high probability of collision between the donor and the acceptor, and hence you can expect to have exciplex or excimer. Okay. So, formation excimer formation is a special case of a general class of weakly bound complexes. Okay. formed between the excited molecule and a ground state molecule. Excimers can be classified as homodimers being composed of identical pair. Exciplex can be written as a heterodimer or a heteroexcimer. Okay. But in case of Exciplex, the pair in constituents in a pair, they need not be identical. In that case, you can have Exciplex. For example, Leonhardt and Wheeler in 1961 observed that the fluorescence spectrum of biphenyl in cyclohexane solution in presence and in absence of diethyl aniline, and in that case a new band has been observed in cyclohexane. Okay. So, so biphenyl in the excited state, okay, this is BP biphenyl in the excited state giving rise to BP star, and then you add diethyl aniline or maybe in absence of that. So, you will get an additional band, okay, and that corresponds to your a new species which I am talking about over here, which is your Exciplex, excited state complex. So, these are all, this Exciplex or Excimer, these are a general class of weakly bound complexes. These are not strongly bound complexes. So, these are weakly bound complexes. These are weakly bound complexes, that is the binding interaction energy wise it is much less compared to true covalent bond formation. So, these are either whether it is Excimer or whether it is Exciplex, it does not matter. These are all weakly bound complexes. Okay. So, you see that for a general for any the spectra which you are seeing over here, it is just a general representation of the fluorescence spectra as a function of wavelength. Okay. And you see that in absence of any quencher, in this case quencher is an electron transferring species. So, what is happening that when you add the quencher, you expect to have an additional band like this, and broad band, of course. This characteristic is broad band. And if you have like polycyclic aromatic compound, like say more than one benzene ring, in that case you can expect to have like this vibrational structure like this in the emission spectra. Okay. So, what is happening that in this case you go on adding more and more quencher, and this is decreasing and you have increasing pattern. Okay. And you see that there is an isoemissive point. This is your, say this is your donor fluorescence and this is your Exciplex. Okay. And this is your donor fluorescence. Now, the point is, you may ask one question that how do you understand why I have used a term Exciplex over here when we are adding, this is your donor emission of course, and this is your quencher increasing, this way quencher also, as you increase quencher concentration it increases. So, you may be wondering why I have started with the term Exciplex, why not Excimer? Now, one point is that since I am using here like one donor and another acceptor, and these two are not the same molecule. That is why it can be Exciplex, and in other case this is your Exciplex band. So, you see that if you think of like they are general in nature, then it is say D plus A minus. It is a charge transfer complex, and it is an ion pair. Okay. So, if you what you do that if you increase the polarity of the solvent, or if you change the polarity of the solvent, I mean solvent in which you are studying the experiment, then what do you expect that as you increase, I mean this donor acceptor, this charge separation will be very much dependent on the polarity of the solvent you are using. So, therefore, this band will be solvent sensitive, and also the fluorescence intensity will also be solvent sensitive. Okay, because if we increase high polarity solvent, then Coulombic interaction, I mean it is Q1 Q2 by epsilon r square. So, if we increase this, then Coulombic interaction will be reduced, and therefore, they will separate. Okay. So, they will separate. So, that means, and they will separate. So, this type of interaction, I mean this type of thing you can expect. So, therefore, this will separate, and and at the same time their relative energy levels, I mean relative energy levels means the energy level between which this, I mean between which the transition is occurring, as a result of which this band is coming, that will also be modulated as a function of the polarity, I mean dielectric constant of the medium. Therefore, I mean polarity variation of polarity of the medium can be important in diagnosing whether in the diagnosis of an Exciplex or an Excimar. Okay. So, an Exciplex will have a generally it is a broadband. If you think of say pyrene Exciplex formation, I am just writing down the gross spectra, not to scale. So, it is like this. Then as you increase your diethyl aniline, it will reduce. Then you are adding steel more. Okay. Then ultimately okay. So, this is growing in height and it is reducing. Okay, this is intensity, this is lambda. Okay. So, this is the typical equilibrium between your donor, and this is your D plus A minus, and this is an isoemissive point. That means that there is an equilibrium. That signifies an equilibrium, that this species is converted at the expense of, I mean this species is formed at the expense of reduction of this species. So, that is why there is an isoemissive point, like isosbestic point in UV visible spectra. This is a typical spectra of pyrene, that this is your pyrene emission and these are Exciplex emission, and you see these are taken at different in different solvents. So, there is a shift. You see that it is completely this pyrene fluorescence is completely washed out when some concentration of your quencher is added. It is a donor, and here actually what is happening, that sorry, in case of pyrin it is an acceptor. In case of pyrin it is an acceptor, and your donor is diethyl aniline or dimethylamine. Methyl aniline. So, it depends. I mean, if you use diethyl aniline or dimethyl aniline, then it will be a donor and this is an acceptor. So, excited donor, sorry, excited acceptor, acceptor in the excited state and donor in the ground state. Okay. Reverse thing may happen, that if you have your different oxidation potential of these two species. I mean, if you choose a particular pair in such a case, in such a way that the oxidation potential is such that one species will act as a donor and the other will act as an acceptor, although in other instance this species may act as a donor and the other one may act as an acceptor. I mean, other means the second species. Okay, like when it is pyrin DMA, then pyrin is the acceptor in the excited state, and if it is something else, then pyrin may act as a donor as well. Okay. So, it depends on the relative this oxidation and reduction potential of this species, or their reduction potential, and it depends on the reduction potential of the ground state as also the excited state species. Although say pyrin in the ground state is not a in this pyrin DMA case, although this pyrin in the ground state is not a good acceptor, but the moment when you excite to pyrin star, then it acts as a good acceptor. So, DMA then transfers electron to this pyrin star, giving rise to pyrin minus dot. So, basically one electron is transferred and DMA plus dot, and then there is the interaction between these two, electrostatic, or maybe there is a Coulomb interaction between these two to bring them close to each other. And I gave you a little idea about this Exciplex fluorescence imaging, that's an emerging technique by which you can just have an image of the distribution of this liquid and vapor phase in the combustion chamber before before this piston is compressed, or maybe after the combustion has taken place. So these this can be used for this type of diagnostics. This Exciplex formation can be used for this type of diagnostics, that in solution Exciplex may be formed, but in vapor phase Exciplex may not be formed. So using that you can get different information, and the idea is that Exciplex is a redshifted emission compared to your original fluorophore emission like pyrin. Pyrin is having emission band which is around, it starts from around 350 to say 450, and your Exciplex emission is around 460 or even after that, depending on the polarity of the solvent. Okay. So, this is the typical energy diagram for your Exciplex formation. So, this side is the potential energy, this is the reaction coordinate, this is your ground electronic state, and this is the excited electronic state. Okay. So, and this is the repulsive potential. So, this part is your A, say star D donor, say this is pyrin star DMA, okay, and this is your pyrin ground state. Excited pyrin first. So, this is your S1 of pyrin, this is S0 of pyrene, and excitation takes place this way, say maybe here, and K1 K minus 1 giving rise to A D star. Then there is charge, charge transfer, and then this is your acceptor is delta minus, this is delta plus, and then you have bound state. This is your exciplex. This particular surface is for your exciplex. So this is bound state, called your exciplex state, having a minima, exciplex having a minima, and your ground state is repulsive. So ground state corresponding to the exciplex, this dimer or this pair of A and A, it is repulsive. So repulsive ground state. Okay. So that means this is quasi static, quasi continuous level. So what happens that when emission takes place, it always ends up to this repulsive ground state, so without any minima. So that means the emission is originated from a ladder to a state having no definitive minima, or having no ladder at all, no levels at all. So it is a continuous level. So therefore this particular case, if you have emission from here to here, then you can have this structured kind of thing, and here you can have broad emission. So this is broad and this is structured. Okay. So this is a structureless exciplex emission. So structureless means broad exciplex emission. Okay. So that is the basic diagram of for the exciplex formation between say pyrene and DMA, where pyrene is initially excited and then DMA quenches that excited pyrene, and thereby generating this exciplex, and then exciplex fluoresces to give you exciplex fluorescence. Okay. Okay. So say for you have this like A star, 1 A star plus D. So scheme wise you can write it over here, that 1 A star plus D giving rise to AD star in the singlet state. Then it gives you A plus D plus H nu exciplex, and it gives you your A plus H nu say monomer. This is the monomer emission, and this is your exciplex emission. This is structured, this is broad. The 1 AD star state is regarded as having a CT character, because it should have a CT character, because in the excited state there is some delta minus character on A and there is some delta plus character on D. So that is why it has a definitive CT character, and there is some interaction between charge transfer interaction. Okay, that is there, and thereby it has a minima. See, there is a minima. Okay. And this exciplex ground state is repulsive, or you can call it as also dissociative. The binding on the S1 surface is made up of 3 energy terms. This is one is E or here I can write E, it is equal to IP of donor, okay, plus electron affinity of the acceptor plus this Coulomb. This Coulomb term is it is the Coulombic term, that brings the ion together because of the Coulombic interaction between them. So once this 1 A star plus D, that interaction takes place, I mean charge transfer interaction takes place, then it gets a definitive charge transfer character. So, and thereby since there is a charge transfer character, so there is a Coulombic attraction. Okay. The experimental evidence that Exciplex fluorescence depend on the reduction potential of both components. The Exciplex fluorescence maxima can be affected by solvent polarity, and this, the expression goes like this, where it is this polarity dependent Exciplex emission. It is related to the Lippard-Mataga relation, that is mu is the Exciplex dipole moment, that is how much charge separated. Separation is there. Rho is the radius of the equivalent sphere, that is in the Onsager reaction field, I mean the radius of the reaction field. Epsilon is the static dielectric constant, n is the refractive index of the medium in which this Exciplex is formed. Okay. So, this is your H nu Exciplex equal to H nu 0 Exciplex, and then this related to the solvent polarity, okay, and of course the radius of the equivalent sphere. So it I mean Exciplex fluorescence depends on the reduction potential, and also as I told you it depends on the solvent polarity as well, that is fluorescence maximum. So this will be a clear cut diagnostic of this, whether it is excimer or Exciplex. So in solvents of high dielectric constant, Exciplex emission is found to disappear, and the transient absorption studies show the appearance of the separated radical cation and radical anions. I mean, the point is, if you have like this, let us think in this way, that you have dA having a definitive this charge transfer character. So, in that means it is your d delta plus acceptor delta minus, then d dot plus a dot minus, and they are much separated, I mean distance increases. So, it is called the solvent separated ion pair or solvent separated radical ion pair. This is your Exciplex. Okay. So, polar solvent. So, Exciplex emission is as a result of this recombination of this, I mean the back electron transfer, so that it comes down, and it is a radiative phenomena. So, if these are taken apart from each other, so then you will not get emission, this Exciplex emission. And if you have the transient absorption study, that if you have a time resolved absorption study, then you can study this one, or you can study this one, this absorption. I mean like the irreversible absorption which you do with respect to the ground state, and if it is a transient species, then you have to have a very short pulse of radiation and then detection procedure, so that you can also see, or you can also feel the presence of, experimentally you can see the presence of this d plus dot or a minus dot, that is solvent separated this radical ions, that they will have long lifetime, that if you can monitor this decay profile of this, then you will be finding that maybe the decay corresponds to this, that even after a long time the absorption remains. Say if it is delta d versus time, then it stays, I mean it remains there for a long time. That means you have considerable amount of absorption even after giving a sufficient amount of time. That means they do not have the option to recombine or do the back electron transfer, so that they remain as it is, I mean as this dot plus or dot minus. And now this exciplex is often found between planar aromatic hydrocarbons like naphthalene, anthracene, phenanthrene, pyrene and aromatic amines. The amines are electron donors, as I told you. Other partners for aromatics can be strong electron acceptors such as cyanoaromatics like dicyanobenzene. Dicyanobenzene, DCNB. DCNB or tetracyano say benzene. Okay. So, these are acceptors. In these cases aromatic hydrocarbons may be the electron donors. Okay. But one important point is that their E0 value in the ground state and excited state should be matched accordingly, so that no ground state interaction is there, but in the excited state there is a definitive interaction and there is a definite minima in the potential energy surface, so that the exciplex formation will be effective. Okay. Exciplex are defined as existing in the excited state only. There is no binding interaction in the ground state, as it is clear from the this potential energy diagram I presented. Some molecules have very strong tendencies to lose or gain electrons in their ground states and form addition complexes without excitation, and these are not exciplex. I mean these are not termed as exciplex. Okay, so these are simple addition complexes. These are called electron donor acceptor complexes, also called the charge transfer complexes, as for example anthracene picric acid that happens in the ground state. Okay, I mean in that case you do not need to excite one of the two, one of them, I mean one of the two, one of these, one of them means either anthracene or picric acid. Okay, so such complexes can also be excited. I mean this anthracene picric acid complex, I mean this complex may be excited, but they are not classified, I mean classified as exciplex, because charge transfer has already taken place in the ground state. So, you do not need to, I mean in order to have this charge transfer you do not need to put them in the excited state, because this already has happened in the ground state. Okay. And their ground state is bound, but in case of exciplex the ground state is not bound. Okay, excited state is bound. Okay. So, this is a typical kinetic scheme for this exciplex formation. This is your K1, this is K minus 1, AD star, of course there is a definitive delta minus delta plus character, then K3, okay, giving rise to A plus D plus H nu in lambda 2. It is a shifted emission, and this is your K2 A plus H nu, of course in lambda 1 plus donor is there. Okay. So, enthalpy is negative, that means there is a binding interaction. So, enthalpy is negative, and if you have, I mean if you just plot I A D star, I mean this emission intensity divided by this emission intensity at two different temperatures, then this relation is found to hold good. I mean that you can deduce that this I A D star by I A star T2 I A D star by I A star at T1, that will be minus delta H by R into 1 by T2 minus 1 by T1. It is a Van 't Hoff relation, and I mean when K1 and K minus 1, these two are very greater than this K2 and K3, that is a rapid equilibrium between these two states, then you can expect that this Van 't Hoff kind of relation will be there. Okay. Now, in that case if you increase temperature, I mean if you plot this as a function of 1 by t, ln this as a function of 1 by t, then you can expect a positive slope. Okay. So, that means with increase of temperature, the fluorescence intensity, since this is delta H is negative. So, fluorescence intensity is expected to decrease. Okay, enthalpy is negative. So, that means the, more dissociation will take place, and therefore, fluorescence intensity will decrease with temperature. But in other case, if k minus 1 is slow, this coming back is slow, that means it is a barrier. For this particular process, this backward process, it is a barrier dependent thing. Okay. So, if we increase temperature, then what will happen? This population will increase. So, this population will increase means, if this population increase, this k1 will increase, but this one, since it has got a barrier. Okay. So, returning here will face some barrier, so that its temporary population will be more, therefore, it will have more emission. So, that is why if k1 is slow, Exciplex fluorescence should increase with temperature. Otherwise, in this case, Exciplex fluorescence should decrease with temperature, because these two are for this case, these two are rapid compared to this. So, if you increase temperature, then not only this one, but this one will also increase. Okay. And as a result of which, overall fluorescence fluorescence of this one will be affected, and with increase of temperature, in first case your fluorescence intensity will decrease. Okay. This is a typical potential energy curve for your locally excited and charge transfer state. Now, I will just take a little time for this spin of electron, because here in this charge transfer case, you have 2 electrons. Okay. And depending on their spin parentage, whether if it is if this radical pair is a singlet radical pair, or if it is a triplet radical pair, okay, the situation will be different. They will have different type of dynamic behavior if their spin parentage is different. If it is a singlet bond radical pair, or if this radical pair, it is basically a pair of radicals. So, if this radical pair is like this, okay, one is up, another is down, so singlet. So, immediately after this formation, they will try to recombine. Okay. So, they will try to recombine means so their separation means before their separation they will recombine. So, first recombination will be there, but suppose if the radical pair is like this, then they will have two things. In order to recombine, they need to have this spin flipping and then recombination, or otherwise it will have tendency to escape the solvent cage in which these two are generated. So, that is why their spin parentage, their spin state is important. It is the radical pair spin state, combined spin state, it is not the molecular spin state. Okay. So, this is your XYZ axis, this is your spin vector. Okay. This is your z axis, this is your projection of this spin vector on this z axis. So, this is your up spin plus up h cross, and this is your minus up down spin minus up h cross. So, if these two are like spin parallel, okay, then these two will have three situations. One is alpha alpha, then beta beta, probability wise alpha alpha, beta beta, or a linear combination of alpha beta and beta alpha. Okay. So, So, it is a linear combination of alpha beta and beta alpha. So, you see that this alpha alpha is called T plus, beta beta is called T minus, because the total spin projection is like this half and this half, means spin projection is minus 1. Here total spin projection is plus 1, because plus up, and here spin projection is your total spin projection. It is ms equal to, I mean, spin projection is z direction is 0. Okay. They are not truly opposed. I mean, one is in this direction, another is in this direction. So that their spin projection is 0. So, you see that alpha beta, I mean for T0 you have this combination alpha 1 beta 2 and alpha 2 beta 1. This is a linear combination of these two, because if you have equivalent situation that such that the electron 1 is alpha, electron 2 is beta, and equally probable situation is electron 1 is beta, electron 2 is alpha. So, that you have to have a linear combination with appropriate normalization constant. So, now what is happening, that this state to this state, I mean if you think of it, and the singlet, for singlet you have this alpha beta truly opposed. You see it is in this direction, it is in this direction, truly opposed. So, that its spin projection is 0. Okay. But here spin projection is 0 on z axis, but its total spin is 1. So, it is called your T0. So, what is happening, that in order to have this situation to this situation, you need to have just changing the angle of this vector. I mean, angle means this angle. I mean if you change its angular frequency, then one situation will be arrived that this will assume this situation, that is one is like this, another is like this. So, if it is doing like this, then it is spin opposite. So, it is your singlet state and this is your triplet T0. So, what is happening, that in presence of an external magnetic field, both will precess. Okay. And they may maintain a constant phase difference, or there may be a possibility of a phase difference. Phase difference may change with time. So, what is happening, that if these two, these two spins, if these two spins precess at a different angular velocity, then one situation will be reached that you may get this situation, or maybe you can switch from this situation to this situation. Okay. So, that is called your singlet to triplet transition. So, and in principle you can have this singlet to triplet transition depending on the external magnetic field. So, you can play with this spin, spin radical pair spins in presence of an external magnetic field. So, details of this I will come with it in a separate lecture, but I am just giving you the idea that this singlet triplet state, radical pair singlet triplet state, this transition, generally singlet to triplet transition for molecular system, you need to have something called this spin orbit interaction. Okay. Spin orbit interaction is spin motion is mixed with mixed with orbital motion, so that, or it is coupled with orbital motion, so that this pure state description is not a valid description. So, in that case your singlet state will be a combination of singlet plus a little triplet, and triplet state will have a combination of triplet plus a little singlet. So, that then the transition from mixed singlet to mixed triplet will be easier. But here what is happening, that you have a radical pair depending on their separation. If they are widely separated, then situation is different, but if they are in close proximity to each other, like within 10 angstrom separation, then they are called spin correlated, and various things may happen. Interesting chemistry may take place because of this spin transition, singlet state to triplet state, or maybe you can reach from here to here by mere flipping the spin from just 180 degree flipping, okay, from here to here. So, that will generate this to that. So, so these are some interesting topic that I am going to take up in some in some other class. So what we have got here, that in Exciplex case, I mean Exciplex is a case of heterodimer formation in the excited state, and in this case you do not have a definitive minima in the ground state. I mean ground state is repulsive and the excited state or the Exciplex state, which is a charge transfer state, is attractive, and it is having definite minima, and it has got this vibrational structure. So that is why from this vibrational structured state, you can emission can take place to this unbound state, and as a result of which you have this structureless Exciplex emission. Okay. So, this structureless emission, and importantly, if you just think of the nature of this particular species, you will be finding that since it has got a charge transfer character, so its emission intensity or this charge transfer emission intensity will be dependent on the polarity of the medium as also the viscosity of the medium. So, if viscosity increases, then it should be affected. If polarity changes, it may be affected. So, that is why this viscosity polarity is very important factor for this Exciplex formation, and it has got potential energy diagram I just showed to you. Now, this Exciplex is a case of, since it is a charge transfer complex. So, the moment when there is a charge transfer, that means it is basically an electron transfer. So, you generate a ion pair. So, ion pair means, so two electrons, and depending on their spin orientation, relative orientation, they can be singlet or they can be triplet. So, singlet or triplet, this is related to the radical pair spin state, it is not the molecular spin state. So, and this singlet and triplet state can have interesting chemistry with external perturbation as magnetic field. So, this Exciplex emission, is a redshifted emission, and this charge transfer process, it grows with time. I mean, if you have a time resolved description, then you will be finding that immediately after photo excitation, you may not get Exciplex emission immediately, but after some time you can expect to have emission which is built up in sufficient intensity. So, that completes our general description related to the Exciplex. So, in the next class we will take up another issue which is called Excimar, and in another session, another session means in another class, we will take up this special issue of effect of external magnetic field on this behavior of this Exciplex emission. Okay. So, that is all for today. Thanks for your attention.